Okay, so imagine shrinking a massive high-res image down to just a tiny fraction of its size.
Yeah.
But, like, you can still perfectly recreate the original. It's kind of like magic, right? That's image
Yeah.
tokenization. And today we're diving deep into this new method that's really pushing the boundaries. GSQ, Group Spherical Quantization. You shared this research paper with me, and I got to say, it's dense. I'll give you that. But the potential here, huge.
Yeah, the potential is really interesting. I mean, GSQ is basically creating this super efficient code for images. And that has huge implications for, well, everything. AI image generation, compression, even how we send images across the internet.
Okay, so break it down for me. What is image tokenization?
Well, think about it this way. We're transforming images into these discrete units of information, like kind of like turning a picture into words and these tokens. They're much easier for AI models to work with than just raw pixel data.
Okay, that makes sense. And it makes me think about JPEG compression. It throws away some data to make the file smaller, right?
Yeah.
Is that related at all?
You're on the right track. JPEG is definitely an example of what we call lossy compression, where some information is lost. What's exciting about image tokenization is that it's pushing towards lossless compression, meaning we can shrink images dramatically without sacrificing detail.
Whoa, that's pretty wild. But I imagine there are some serious challenges to make this work. Where do things get tricky?
Well, you're right to be skeptical. One of the biggest hurdles is balancing that compression with image quality. The more you shrink an image, the harder it is to keep all that detail, all those tiny nuances. And then as you increase the complexity of the image, you run into this issue of, well, how do you represent that information accurately? These are what we call high-dimensional latent spaces, and they can be really tough to work with.
It's like trying to stuff this giant, sprawling map into a tiny suitcase. The more you fold and cram it in, the harder it is to make sense of it later.
Yeah, that's a good way to put it. And that's where GSQ comes in. It has this really clever approach. Instead of just folding the map haphazardly, we're carefully dividing it into these smaller, more manageable sections.
Okay, I'm intrigued. So tell me, how does this grouped approach actually work?
Okay, so imagine you have this massive image file, and each pixel is represented by like this long string of numbers. What GSQ does is take that giant string of numbers and breaks it down into smaller groups. It's not just random division either. These groups are created strategically to make the information easier to handle.
So instead of dealing with this overwhelming mass of data all at once, we're breaking it down into bite-sized chunks.
Exactly. And that's where the power of GSQ really starts to shine. By processing these smaller groups independently, we can actually improve the accuracy of the whole process, like assigning a team of specialists to each section of that map, instead of having one person try to decipher the whole thing.
Got it. But what about the spherical part of GSQ? What makes that so important?
That's where things get really interesting. So instead of just thinking about these groups of numbers as points in a typical flat space, GSQ maps them onto the surface of a sphere.
So like plotting constellations on a globe instead of a flat piece of paper.
Exactly, you got it. And the seemingly simple shift to a spherical representation, well, it has some really profound implications. For one, it helps to avoid those cursive dimensionality issues we talked about. In a high-dimensional space, everything starts to look the same, like it's all blending together. But on a sphere, things stay distinct, even in those higher dimensions. It's like creating more breathing room for the information.
So by thinking spherically, we're basically finding a more efficient and accurate way to represent all that complex image data.
Exactly. It's a bit mind-bending, but incredibly effective. And what's even more impressive is that GSQ achieves all this without relying on overly complicated methods. It's surprisingly elegant and efficient.
Now I'm curious about how this actually translates into real-world performance. The paper mentions some pretty impressive results. What kind of improvements are we talking about?
Well, GSQ consistently outperforms other state-of-the-art methods. They were able to shrink images down by a factor of 16, that's 16x smaller, and still get incredibly high-quality reconstruction.
16x smaller. I'm having trouble wrapping my head around that level of compression. What did the reconstructed images actually look like?
Well, they used a metric called RFID to measure the quality of the reconstruction.
Yeah.
And with that 16x downsampling, they got a score of 0.50.
Okay, I'm going to need you to break that down for me. What does an RFID score of 0.50 actually tell us?
Think of RFID as a measure of how closely the reconstructed image matches the original. The lower the score, the better. And 450 is incredibly good, especially at that level of compression. It basically means you'd be hard-pressed to tell the difference between the original and the reconstructed image.
Wow, impressive. And they were able to go even further than 16x, right?
Right. They managed to go all the way up to 32x downsampling, which is pretty unheard of. It really highlights the potential of GSQ to handle just incredible levels of compression without sacrificing image quality.
Okay, now I'm really starting to see why this is such a big deal. But what's the secret sauce here? What makes GSQ so effective at achieving this?
Well, one of the key factors is the size of the vocabulary that GSQ uses. Imagine a code book filled with visual patterns. The bigger the vocabulary, the more nuanced the representation of the image.
So it's like having a richer language to describe what we're seeing in the image.
Exactly. And what's really interesting is that they found a model with a relatively small processing space, but a huge e-vocabulary, like 512,000 words, and that performed the best. It kind of challenges the assumption that bigger is always better.
So a smaller, more specialized system can sometimes be more powerful than a larger, more general one.
It seems that way. And this ties back into the efficiency of GSQ's grouped approach. Smaller, carefully organized groups of information. They're often easier to work with and lead to more accurate results. It's about finding that sweet spot between complexity and efficiency.
This is all incredibly interesting.
Mm-hmm.
But I'm also wondering about the practical implications here. We've got this powerful new method that can handle these incredible levels of compression without sacrificing quality. What does this mean for the future of things like image generation?
The potential here is truly vast. GSQ's ability to handle increasingly complex images with such high efficiency, well, it makes it ideal for a whole range of applications. We're talking about everything from revolutionizing how we store and transmit visual data to creating entirely new ways to generate and manipulate images.
This is getting me really excited to explore the potential applications of GSQ. But before we get ahead of ourselves, I think we need to take a step back and dive deeper into how this whole process actually works.
Yeah, you're right. Let's break down some of the technical details of GSQ. We've talked about the what, but now let's get into the how.
Okay, let's unpack some of the nuts and bolts of this fascinating technology.
One of the key innovations in GSQ is how it handles this thing called the codebook, which is essentially like a dictionary of visual patterns.
Right, we touched on that a little bit earlier. It's like the vocabulary that the AI model uses to understand and represent the image. But how does GSQ actually build and use this codebook?
That's a great question. So the codebook contains a set of these predefined, what we call code words. And each of these code words represents a specific visual element or feature. Think of it like a visual alphabet.
Okay, I like that. So instead of using letters to form words, we're using these code words to build up an image.
Exactly. And during this quantization process, each of those groups of numbers we talked about, those points on the sphere, they get matched to the closest code word in the dictionary.
So the algorithm is basically searching for the best visual word to describe each chunk of the image.
Yeah, that's a good way to think about it. And the size of the codebook, or the number of code words, well, it plays a crucial role in the overall performance of GSQ.
We talked earlier about how a larger vocabulary led to better performance in the research. But is there a downside to having this massive codebook?
That's where things get interesting. You might think that a bigger codebook is always better, but it's not that simple. A larger codebook requires more computational resources to process and manage.
So there's this trade-off between having a rich vocabulary and, like, keeping things computationally manageable.
Exactly. And that's one of the things that makes GSQ so clever. It manages to achieve this excellent performance with a relatively small codebook, thanks to the way it groups and processes information.
Well, not just about brute force, right? It's about finding those elegant and efficient solutions.
Precisely. And the researchers actually went even further, and they experimented with different ways to initialize and refine the codebook during training, and they found that using a technique called k-means clustering, well, it led to some significant improvements.
Okay, I have to admit, some of these technical terms are going a bit over my head. Can you break down k-means clustering for me? Like, what is it and why is it so helpful here?
Sure. Imagine you have a scatter plot of points, and you want to group them into clusters based on their proximity to each other. K-means clustering is an algorithm that does exactly that. It finds the best way to group those data points into a predefined number of clusters.
So in the context of GSQ, it's helping to organize the codebook in a way that makes it easier to find the right code word for each piece of image data.
Exactly. It's all about optimizing the structure and content of the codebook to improve the accuracy and efficiency of the whole process.
Okay, that makes a lot of sense. Now, the paper also mentions downsampling a lot. We've kind of touched on this, but can you remind me what downsampling is and why it's so important for image tokenization?
So downsampling is essentially the process of reducing the resolution of an image. Instead of having this grid of pixels with a one-to-one mapping to the original image, we're creating this smaller, more compressed representation.
And the more we downsample, the smaller the file size, but the greater the risk of losing detail, right?
Right. It's a delicate balancing act. And GSQ's ability to handle these high levels of downsampling while retaining image quality, well, it's one of its most impressive feats.
The paper highlights those impressive results with 16x and even 32x downsampling. But how does GSQ actually manage to do this without sacrificing detail?
It all comes down to how GSQ combines those three core innovations we've been discussing: grouping the latent space, mapping it onto a sphere, and optimizing that codebook.
So it's like the synergy of these techniques that allows GSQ to push the boundaries.
Precisely, by working together. These techniques allow GSQ to represent complex visual information in a highly compressed form without losing those crucial details.
This is making me think about data storage. Like if we can compress images down to a tiny fraction of their original size without losing quality, that could totally revolutionize how we store and manage these massive image data sets.
Absolutely. Think about the implications for fields like medical imaging, where they're dealing with these incredibly large, high-resolution scans. GSQ could allow them to store and access those images much more efficiently.
And what about how we transmit images over the internet?
Well, imagine a world where you can stream 4K movies instantly, without any buffering, even with a slow internet connection. That's the kind of future that GSQ could enable.
It's mind-blowing to think about how this technology could transform our relationship with visual information. But I'm also curious, are there any limitations to GSQ? Are there certain types of images or applications where it might not be as effective?
That's a great question, and it's important to remember that no technology is perfect. GSQ is still a relatively new approach, and there's always room for improvement. The researchers themselves acknowledge that there are challenges and areas for future exploration.
So where do they see the biggest opportunities for further research and development?
Well, one area they highlight is the potential for developing even more sophisticated codebooks. Like we discussed, the codebook is such a crucial component of GSQ, and finding ways to optimize its structure and content, well, it could lead to even better performance.
It's like refining the language that GSQ uses to describe images.
Exactly. And another area for future research is exploring how GSQ can be applied to different types of images and visual data.
Right, we've been focusing mainly on still images. But what about video? Or 3D models? Could GSQ be adapted to handle these more complex forms of visual data?
Those are great questions, and I think there's a lot of potential there. The researchers are already exploring how GSQ can be extended to handle video compression, and the early results are promising.
That's exciting. It seems like we're just scratching the surface of what's possible with this technology. But before we get carried away with the future, I think it's important to acknowledge just how impressive GSQ's current capabilities are.
Absolutely. The fact that they were able to achieve such high levels of compression with such minimal loss of detail, it's a remarkable achievement.
And it all comes down to some really clever thinking and innovative algorithms. It's a testament to the power of human ingenuity to solve these complex problems.
It's a reminder that there are always new ways to look at things, and that breakthroughs can often come from these unexpected places.
This deep dive has definitely been an eye-opener for me. I'm starting to see the world of images in a whole new light.
I'm glad to hear that. It's fascinating to think about how this technology could change the way we interact with visual information in the years to come.
But before we get too far ahead of ourselves, I think it's time to bring things back down to earth a little bit and explore some of the potential real-world applications of GSQ. We've talked about the possibilities in these abstract terms, but let's get specific. How could this technology actually impact our lives in the years to come?
That's a great point. Let's delve into some concrete examples.
We've talked about GSQ in this theoretical sense, but let's bring it down to earth. How could this technology actually impact our lives, like in practical ways?
Well, one area I think where GSQ could be a real game changer is the world of streaming. Imagine being able to stream like 4K movies instantly, even with a slow internet connection. No more buffering, no more waiting.
That would be amazing. And it's not just about entertainment though, right? Think about things like telemedicine or remote education.
Exactly. High-quality video streaming, it could become accessible to anyone, anywhere, regardless of their internet speed. I mean, this could revolutionize healthcare in remote areas, make education more accessible, even transform how we work.
It really shows how these technological advancements can have a ripple effect across so many aspects of our lives. And it's not just about transmitting data, it's also about how we store it. We're generating so much visual data every single day. Photos, videos, medical scans, satellite imagery.
And with GSQ, we could potentially store all that data so much more efficiently. Imagine storing an entire library of high-res images on something the size of a thumb drive.
That's incredible. It would revolutionize everything. Cloud storage, personal archiving. But what about the computational side of things? We've talked about how GSQ is efficient,
Yeah.
but compressing and decompressing images at this level, it's got to require some serious processing power, right?
That's a good point. The computational demands of GSQ are something to think about. But as computing power gets better, those demands are likely to become less of a barrier.
So we could see a future where GSQ is just integrated into all our devices, handling image compression and decompression in the background.
It's definitely possible. As the technology gets more mature and more widely adopted, we can expect to see hardware and software optimized for GSQ, which will make it even better.
This makes me think about AI. AI models are incredibly data hungry. Could GSQ play a role in making AI more efficient and accessible?
Absolutely. By compressing visual data so effectively, GSQ can make it so much easier and faster. For AI models to process and learn from those massive data sets, this could lead to huge advancements in areas like computer vision, image recognition, even natural language processing.
It's exciting to think about how GSQ could help unlock the full potential of AI. But as with any powerful technology, there are some potential downsides, ethical considerations to keep in mind.
You're right. It's crucial to be mindful of the potential risks. For example, like we talked about, the ability to compress images so well could raise concerns about authenticity, deepfakes, and other forms of manipulated media. They could become even more difficult to detect.
That's a scary thought. It really underscores the need for responsible development and deployment of this technology and educating people about the potential risks.
I completely agree. It's crucial to have these conversations about the ethical implications of GSQ and develop safeguards to prevent its misuse.
This deep dive has been a real eye-opener. I'm seeing the world of images in a whole new light.
It's been fascinating to explore the world of image tokenization and these remarkable innovations that are shaping the future.
And as always, we encourage our listeners to keep exploring these emerging technologies. The research paper we talked about today is a great place to start. If you want to learn more about the details of GSQ,
And we'll be sure to include a link to that paper in the show notes. For now, we hope this deep dive has sparked your curiosity and inspired you to think about the future of images in a new way.
until next time, keep exploring, keep questioning, and keep diving deep.